Hello everyone. In last class we discussed the series RLC circuit, series resonant circuit. So in this class we are going to discuss the parallel resonant circuit or anti-resonance. So a parallel circuit is said to be in a resonance when the applied voltage and current both are in phase or the power factor is unity. The idea behind the resonance is same, either parallel or series. The voltage and current both are in phase or power factor cos pi should become unity. That means whenever phase angle is between voltage and current are in phase or it is 0, it will become automatically 1. Now consider the parallel resonant circuit with applied voltage of V and total current I. Let us assume here the circuit is resistor. What is the meaning of parallel? Means these energy storage elements both are should be in parallel. That is the idea here. And applied voltage, let us assume the alternating voltage V and the current is I, and the current through the circuit here is IL, and in this path it is IC. So we know that the condition for resonance XL equal to XC, inductive reactance equal to capacitor reactance, but here it is a parallel. That's why we can say that susceptance should become 0. So if you find the admittance of the branch containing L and RL is given by, let us assume the first branch admittance I am taking YL equal to 1 by RL plus J into XL. If you take the rationalization and everything, we will get RL minus J into XL divided by RL plus omega square into L square. Means if you substitute in the place of XL J omega L, we will get R square plus omega square L square. So the admittance of the second branch, the capacitance is given by YC equal to 1 by minus J omega XC. So J by XC, that is equal to J into omega C. Since the total admittance Y of this parallel resonant circuit is Y equal to YL plus YC, there we can get RL minus J into omega L divided by RL square plus omega square L square plus J omega C. Now if you take the if you make some terms common here, RL divided by RL square plus omega square L square, if you make common, plus J into here simply we are taking some LCM term, omega C minus omega L divided by RL square plus omega square L square. So I mean that here we are simply separating the imaginary and real terms. Why? Because we know that if you want to prove that circuit is in resonance, total imaginary part should become 0. So at resonance, the imaginary part, the susceptance should become 0. So omega C minus omega L by R square plus omega square L square equal to 0. That means omega C equal to omega into L by R square plus omega square L square. Now if you make cross multiplication, C square plus R square, C into R square plus omega square equal to L. So R square plus omega square L square equal to L by C, where omega square L square equal to L by C minus R square. So where omega square equal to 1 by LC minus R square by L square. So finally we will get the parallel resonance omega is equal to 1 by LC minus R square L square. If you make it in the frequency form, the resonant frequency of parallel resonant circuit is 1 by 2 pi 1 by LC minus R square by L square. This is the resonant frequency of the parallel resonant circuit. So the parallel resonant circuit is possible as long as 1 by LC is greater than R square by L square, otherwise it will be imaginary. So this is one of the very common circuit what we are going to use in the parallel resonant circuits. So the impedance of the circuit can be obtained by putting susceptance part equal to 0 in the expression. By using that equations we can find the terms. If at all resonant frequency is given, we have to find any one of the parameter, either L or C. Like such type of conditions we have to use this mathematical formula. Next, what is another type of circuit we can take in the parallel resonant circuit is There in previous circuit we assumed only one resistance in series with the inductor. Here one more circuit is, I am assuming, two resistances. This I am assuming as a RL and this assuming as a RC. This is L and C. So now this is also one type of arrangement we can consider in the parallel resonant circuit. So the idea is same. And what is the idea? What is the total admittance? First of all, we have to find the individual admittances. YL equal to 1 by RL plus J into omega L. If you rearrange this equation, we will get RL minus J into XL by R square plus XL square. Likewise, here Y is equal to 1 minus RC minus J into 1 by omega C. If you make sure that this one is RC plus JXC by RC square plus XC square. Now the total admittance of the given equation is Y equal to YL plus YC. So that is equal to RL minus J into XL by RL square plus XL square one term plus RC plus JXC divided by RC square plus XC square one term. Now we have to make sure that the imaginary part should become 0. So in order to that, we have to multiply and make sure that separate the imaginary part. RL divided by XL square plus RL square plus RC divided by RC square plus XC square will become real part plus J into XC by RC plus XC square minus XL divided by RL square plus XL square. Now we know that in order to take the condition of the resonance, make sure that the susceptance part is 0. Then we can say that XC divided by RC square plus XC square minus XL divided by RL square plus XL square is equal to 0. Now XC by RC square plus XC square equal to XL by RL square plus XL square. If you rearrange these equations, we will get the resonant frequency. This type of series, parallel resonant circuit, we will get 1 by 2 pi root LC square root of RL square minus L by C divided by RC square minus L by C. If at all any circuit having the resistance in series with the capacitance, then we have to use this formula to get the resonant frequency of the parallel resonant circuit. So in parallel resonant circuit, we have two different circuits. Resistance in series with inductance and single capacitance in another branch, or two resistances are existed in the series L and series C. So this is the way we can find out we can calculate the resonant frequency for parallel